Thank you. Thanks, Andy, for the introduction, and thanks, Dennis, for inviting me here. Today we're going to talk about my attempt at building a superscalar out-of-order processor for an it's really, I wanted to build a processor, and the FPGA was kind of an excuse to do so. First about myself. So I'm currently a CPU architect at Intel in Hillsborough. I started there about a year ago, and I did my PhD at the University of Toronto before that. So today's talk is going to be about the work done at U of T during my PhD. So I'm going to split this talk into basically two major parts. I'm going to first start with some motivation, why we want to build this processor, why I chose x86, and then go through, just the high-level overview of what I did and what the final results were. And then I'm going to jump into a second part of the talk that goes into more details about the actual microarchitectural decisions, how the microarchitecture of the processor actually looks. So I'm going to split this up into two sections. All right, I'm assuming most people here know what an FPGA is already, but just in case, I'm going to give a very brief overview of the way I see an FPGA. So an FPGA is a digital circuit. Like all other digital circuits, it is basically a collection of logic gates hooked up with wires. The nice thing about FPGAs is that they are field programmable, which means you don't have to fabricate them in the factory. The circuit actually doesn't get written until power up. So how do they do that? They basically prefabricate everything you will ever need on the chip, and then put in a bunch of switches, and then you'd get to choose what to connect. But at the end of the day, it is still gates and wires. You just choose whether to use the wire or not, instead of choosing whether to put the wire on the chip or not. As you'd imagine, prefabricating everything has a pretty big cost. So FPGAs for an equivalent circuit is somewhere around 20 times bigger and 20 times slower than a highly tuned custom circuit built directly on silicon. If you look at the diagram, on the left I have what you wanted to build was the logic gates and a few wires. On an FPGA, you prefabricate all the wires with a whole bunch of switches, and now you have to pack your circuit onto that FPGA, being constrained to whatever the resources the FPGA gives you. So wires are prefabricated. There are switches. The logic gates are somewhat more coarse-grained. They use lookup tables, which is basically a truth table. So now instead of having AND gates or gates, you have this flexible logic gate that can become any logic function of a certain number of inputs, 6 inputs being very common. So on modern FPGAs, typically it's 6 inputs. So from the perspective of how you design things for the FPGA, one, it's slower. Two, you now have to be careful about whether your circuit fits into the coarse-grained lookup tables that they have on the FPGA. If they don't, your circuit will still work, it's just less efficient. So you don't have quite as much flexibility as if you had a raw piece of silicon. Okay, so an FPGA is a circuit. It can build any circuit. That includes processors. It may not always be the most appropriate, but it's able to do it. So what do people use FPGAs for? Usually they don't use it to build a processor. They usually have a big digital system, data paths, other things. But they often do still want a processor to do control logic or something like that, something that's flexible and not easily put into a block of hardware. So mainly for laziness. So that means you might want a processor as part of an FPGA, as the entire FPGA. And sometimes that would be a soft processor. So if you need more performance, on an FPGA, the classical way of doing things would be, okay, I'm going to build more custom hardware to make my system go faster. But if you really want to be lazy, if we made the processor go faster, you could get an improvement in system performance with going through less effort at designing custom logic. You might be able to get away with less of this logic if your processor was magically faster. So that's the motivation for why we might want a faster soft processor. All right, so FPGA vendors actually provide some fairly well-optimized soft processors, but currently they tend to be small in-order single-issue pipelines. They are small, but they also tend to be fairly well optimized, so they actually run at a fairly high clock rate for an FPGA circuit. So at the bottom, I have some other examples of soft processors that weren't from the FPGA vendors. And the general trend you see is that those that weren't highly tuned tend to have a fairly low clock rate. And regardless of what microarchitecture you use, if you're giving up 50% of your clock rate, you're not really going to be competitive. So
they also put embedded ARM processors running at much higher frequencies.
They do.
Actually on the FPGA.
Yes, they certainly do. So that's a separate topic, and I would say it is a competitor to soft processors. So if you have a hard processor, you may be less willing to use a soft processor. Okay, so let's suppose you do want a faster soft processor. Given that the vendor-provided processors are already very fast in clock speed, the only way you're going to get more performance out of it is to get parallelism. You're not really going to be able to improve on the clock speed. So there are many ways of getting parallelism. Thread and data level parallelism have been tried in soft processors before, but I like instruction level parallelism because the user doesn't have to do anything. It just magically works. But on the other side, the processor designer has to spend a lot more effort than on the other two styles of parallelism. So I'm going to go down the instruction level parallelism route. So the challenge for me is, can I design a microarchitecture and the circuit, the FPGA circuit, to implement that microarchitecture so that I can get a significantly higher number of instructions per cycle without a significant decrease in clock speed, so that I get an overall performance improvement at an affordable hardware cost and without getting the user to rewrite their software. So I believe the answer is yes. And if you look back in history, the first out-of-order hard processors typically got somewhere about 50% improvement in IPC with basically no change in frequency. So this is the first out-of-order versus the previous generation. So I'm hoping I can get this on an FPGA as well. So now if we're going to build a processor, well, let's first decide on an instruction set. So you already know the answer. I decided to do x86. But why wouldn't you want to do an x86? The most obvious reason is some of these x86 features are really hard to implement. Variable length instructions need length decoding, and x86 encoding is really hard to find out the length of the instruction. So it's doubly bad. Self-modifying code is surprisingly hard to get correct. There are a few instructions that have two destination operands, so that just makes things complicated. But as it turns out, when you're building a processor for high performance, it turns out most of the really hard features actually aren't x86 specific. So another problem with using an existing instruction set is that if you happen to come across a feature you don't like, you don't have the option of saying, we'll change software to work around it. So one example that I suffered through was the floating point unit. I didn't want to build a floating point unit, but I also couldn't change the existing operating systems to get them to emulate the floating point. So that means I have to design an emulation system that was completely transparent from the operating system. That was very painful. So this isn't quite x86. It's when you can't change the instruction set, there's some pain you're going to have to go through. Of course, a lot of people not too far from here are going to be asking, why not RISC-V? It didn't exist when I started this project. That's my excuse. But I also question whether RISC is even the right design, even if you had to start over. I'm not really going to talk about this point in this presentation, but I have some thoughts on it. Okay, so why would you want to implement x86? My answer is it's very easy to implement. Not the hardware, but compared to implementing all of the software that goes along with it. So I found a quote from one of the RISC-V people saying that they were suffering through a lot of pain trying to get benchmarks, and I was like, I will just use the pre-built binaries because it works. So there's a lot of legacy software out there, benchmarks, operating systems. Web browsers are really complex pieces of software that are instruction set specific because of the JavaScript JIT. So these are really, really hard to port to a different instruction set. There's even software in some really unexpected places like your VGA card BIOS. The alpha systems actually had to do x86 emulation just to be able to use commodity graphics cards because there's a little bit of x86 software in the firmware. So it's really the software legacy that motivates x86. And even after going through all of this, I still can't do any of this large software thing. I can implement x86, which is easier than implementing any of this software, my opinion. Okay, so if we're going to build soft processor, so we've decided we're going to build a soft processor. This is the goals that I set out to achieve. I wanted to build a 2-issue out-of-order processor, just so I could call it Superscalar. I wanted good improvement in IPC. So let's aim for 2x what Altera's single-issue in-order soft processor could do. Let's try and improve a little bit on the frequency, but I didn't actually manage to achieve that. So that was a goal that was not achieved. I also chose the x86 instruction set and made sure that I didn't have to rewrite any of the software. So it should be binary compatible with all of the existing operating systems and programs and so on, including system mode. So I ended up actually testing with 16 different operating systems and a whole bunch of user level benchmarks.
So it's just 32-bit, it's not 64-bit.
Right.
Okay.
So I was targeting the P6 instruction set, Pentium Pro. 64-bit is another huge block of the instruction set because it requires all the vector extensions and so on. So let's start with 32-bit for now. Okay, so all right, so let's design a processor. So the first thing you want to do is, I'm building a processor for an FPGA. There is a whole bunch of literature on how you're supposed to build processors. How is an FPGA different from what everyone else is doing? If the FPGA looks exactly the same as regular silicon, well, we'll just build the same processor and call it a day. So let's start with looking at how FPGAs are actually different from custom logic on silicon. So this is a study where I compared it's basically literature search on published papers on custom silicon versus what I can build on an FPGA, and I compared the area and delay, clock speed, of various circuit parts and also some open source processors that have commercial implementations. So if you compare whole processors, I think I compared like OpenSpark. There was a Pentium that was also synthesized on an FPGA. So on average, whole processors are about 22 times bigger and 22 times slower when synthesized for an FPGA than their original custom commercial implementation. So if it's just bigger and slower, that doesn't tell you how you might need to adapt your design to fit the FPGA. So I broke that down into, let's take some common circuit styles and see which ones are particularly bad and which ones are particularly good, and that might influence what I might want to design. So it turns out that for the various circuit types, the delay didn't really vary that much. FPGAs were slower, but more or less uniformly slower, except for SRAMs. SRAMs were particularly a little bit faster. But the big difference was in area. So things like random logic, multiplexers were particularly inefficient. Multi-ported memories were inefficient, CAMs. But circuits that have hard block support on FPGAs, so FPGAs have hard RAM blocks, they have hard adder carry chains. The circuits that use these blocks tend to be particularly area efficient. So my conclusion just from looking at this is, at a high level, because the delay variation wasn't all that big, my conclusion was you can probably get away with a fairly conventional processor microarchitecture. You just have to be a little bit careful to avoid or reduce the size of the expensive components and use a little bit more of the cheaper components. So that made influenced a few microarchitectural decisions. For example, it was decided to use a physical register file instead of a reorder buffer that stored data with reservation stations.
There's a question over here.
Oh, sorry.
You show the whole processor as 22x,
Mm-hmm.
and everything here you show is greater than 22x. So for it to average 22x, there's got to be stuff that's less than.
Are you talking about area or delay? Are you talking about area or delay?
Either one, because everything is greater than 22 on this chart.
No, no. These three are high, but these three are low.
I'm not reading it correctly?
So multiplexers, multi-ported RAMs, and CAMs are very high in area, the red bars.
So is the far left 2.2 rather than 22?
This is 2.2. 22 is in the middle.
Reading the chart. Thank you, I'm sorry.
Yeah, sorry, yeah. It's a log chart, factors of 10, 22 in the middle. Okay, so it was decided to use physical register file instead of storing the data in the reservation stations because that keeps the data in RAMs rather than in a CAM, so that's more efficient. It also makes more sense to have low associativity caches because that requires RAMs rather than a big CAM. So the cost of CAMs influences some of the microarchitectural decisions. Like all of these choices have been used successfully in commercial processors, but I think on an FPGA, certain choices are more preferred. So these aren't particularly strange decisions. They're also used in commercial processors. Okay, so now that we know how the FPGA is different, let's start designing the processor. So this is the methodology I followed when I designed the processor. So I started off with a functional simulator, Box. Are all of you familiar with Box, roughly? It's an open source x86 functional simulator. So again, because it's x86, I can use this as a golden reference model, and I didn't have to write it myself. So I started off with a functional simulator. I then went and replaced the CPU model inside the simulator with a detailed timing model and functional. So I replaced the entire CPU, and now it has timing models, so I know how fast it goes. But it continues to use the simulation of the display, disks, everything else around the system. So I was focusing just on the processor. And the detailed CPU model was informed by the FPGA architecture that I just talked about. And then I took another copy of Box, ran it in parallel, and now use this as verification as the golden reference model. So now my functional and timing model needs to retire the same instructions with the same results as the functional reference model. So I run a whole bunch of workloads, boot a whole bunch of OSs in parallel, and I compare the results, and I make sure my microarchitecture actually produces the correct results. And when I'm satisfied with that, I will then take the detailed model and start building circuits based on the microarchitecture that I came up with. So final answer, the microprocessor that I ended up with is a fairly typical x86 pipeline. So, it starts with instruction fetch. It fetches 8 instruction bytes per cycle. It doesn't know what the instructions are, it just fetches 8 bytes. Then it goes through a whole bunch of length decode stages. It tries to figure out where the instructions start and splits them up into instructions. So in this case, there are 3 instructions in this 8-byte block. It then chops up the bytes and sends them to decoders. Each decoder handles each instruction, and now you can do them in parallel. The decoder decodes the instructions into microops. The microops are then go through a fairly typical register renamer. It just replaces all of the logical register numbers with physical register numbers. And now it goes through a scheduler, which schedules instructions based on whether the operands are available. And then after they execute, the instructions are committed in program order. So it's very classical x86 pipeline. Yes. So you can't avoid it, but there are things like I will try and reduce the size. I will not put the data in the CAM.
You can avoid it. They're just convenient.
They are. I have seen some papers where you avoid it, but you pay an IPC, and it's also really hard to design, and not quite worth the effort. Okay, so the summary of going through all of this is that the main challenge of every single stage was, let's trade the circuit complexity and delay and size with various other things. And in the front end, it's mainly I need to support the common case fast without spending too much hardware to support all the corner cases. The scheduler, it's trading off circuit complexity with capacity. Execution units is trading it off with latency. So it all boils down to, how fast can you make your circuits go? You can come up with a microarchitecture, but you have to spend a lot of effort making these circuits fast. So later on, you'll see a lot of effort on the circuit design in the second half of the talk.
So what percentage of a high-end Xilinx FPGA that would your design take up? Do you have to minimize the amount of hardware?
I didn't try too hard to reduce the area, but the end result is it's, like 7% of a 40 nanometer FPGA. It's like 1% of one now.
So it's tiny.
It's tiny. So yeah, so I just got to the results slide where I will be talking about this. So here is the final result. So I didn't quite get the processor finished. So it's a collection of parts and some projections on what I think the final processor would probably take up. So this is a caveat. These numbers are not. Take these with a grain of salt. So at the end, all this area adds up to something like 29,000 ALMs, which is Altera's logic unit. If you compare it to Altera's processor configured with fairly large caches and so on, typical what you might want from a higher end version of the Altera, just to make my number not look so bad, it's like 6 or 7 times bigger in area and about 20% slower in clock speed. But because the existing soft processors are so tiny, it is really only 7% of a Stratix 4, which is, I think, like 3 generations back at this point. We're at Stratix 10 right now, and I think it's about 1.5% of a Stratix 10.
How much bigger would it be if it were 64 bits?
64 bits or 64 bits x86?
64 bits x86.
I
Hog, nothing but the hog.
I expected it's much, much bigger. It's not the 64-bit that's big. 64-bit would double your data path and so on. But 64-bit also requires 128-bit vector operations and a whole bunch of floating point stuff. So I expect it's much bigger.
Order of magnitude.
I would say somewhere about 5 to 10 times. There's also a bunch of microarchitecture decisions that won't work in x86 in 64-bit. For example, I tuned my front end to decode, say, up to 1 prefix byte, and assumed most instructions were about 3 or 4 bytes long, and 8 bytes and longer were very rare. But 64-bit adds more prefix bytes to the beginning, so I would have to redesign the decoder to handle 2 prefix bytes is now a common case instead of a rare case. So there's a whole bunch of other things that you would have to change.
So, but it would still fit easily on a current high-end Stratix.
Yes, I think it would very easily fit.
Yeah.
But I think my main concern is how much clock speed are you giving up?
Ah, yes.
Because when I was designing this, I was actually focusing much more on clock speed than area. Because I think clock speed is much harder to get, and we have a lot of area. So area is not the constrained resource here. So I don't have a good estimate of how fast you can clock a 64-bit version of this, or what kind of changes you might need to various places to make it work. All right, so area is 7 times bigger, but still small. Frequency, it is currently limited by the memory system. The memory system was the most painful thing to design in this processor. But it is currently the Fmax limit, but I think it should be fairly straightforward to repipeline this to get to trade more clock speed for an extra cycle of L1 hit latency. So it is possible to get more frequency here. Also interesting is that the stuff you would normally associate with out of order, the register renamer and the scheduler, those are actually the fastest units that I had. So if you're thinking of building a out of order non-x86 processor, this kind of suggests to you that maybe it's not such a bad idea. So we're losing on area, we're losing on frequency, I'm hoping to gain on IPC. So here is a plot of SpecInt 2000, only those components that don't use much floating point, because I didn't have a floating point unit. So this is just the integer portion of the SpecInt. So in yellow is the IPC, or the per clock performance. I had to normalize it to per clock performance because there's Nios and there's ARM here, so IPC doesn't work. Right, there are 3 different instruction sets in here. So in yellow is I'm making everything relative to my processor. And, well, first thing is, the reason I have so many processors to compare to here is because all of them are x86, and I could just copy the binaries and run them. It took very little effort. If these were all, so the Nios data point and the ARM data point took much more effort to get because I had to port the benchmarks over. So this is another advantage of using a popular and existing instruction set.
Some of the atoms were actually prototyped in FPGAs, weren't they?
There was a paper on synthesizing the atom, but that was after the fact.
Okay.
So it wasn't prototyped, it was they built the atom, they released it, and then, okay, we'll take the RTL and we'll try and fit it on an FPGA.
Which one was Larrabee?
The failed GPU, x86 GPU.
Okay.
That part I didn't know, but
That didn't involve, I don't think they were prototypes, but they could have been.
so I'm only aware of the published paper on atom, and that was done after the fact.
Right. Okay.
Okay, so in this chart, I also listed the clock speed of the processors. Because this is per clock performance, I only listed the clock speed so to give you an idea of what the expected memory latency would be. So for example, a processor with a native clock speed of 100 megahertz sees a very different memory latency than a processor at 3 gigahertz. So given all these processors, I chose 3 interesting comparison points. The first comparison point is with Nios. That's our stated competitor here. Let's compare to the existing soft processor. We're getting fairly good improvement in per clock performance, about 2.7x. And if you multiply that with the loss in frequency, we're still more than 2 times faster than a Nios. Another interesting comparison point is the Pentium Pro, because it turns out at the high level, a Pentium Pro actually looks a lot like the processor I'm designing. It's also, Pentium Pro is 3 wide, mine is 2 wide. It has basically the same cache sizes, 8K, 256K. I chose the same cache sizes as well. And the IPC is actually not too far, not too different. So, and then another interesting design point is the more recent Atom out-of-order Silvermont. I think that's the first out-of-order Atom. And I get basically the same IPC, but I think the Atom is actually a better microarchitecture than mine because it is seeing a much higher memory latency. So it has much bigger caches, and it has to deal with hundreds of clocks of memory latency instead of 20 or 30. But the end result is the IPC looks pretty much the same. So, I think I can conclude that my microarchitecture design wasn't all too bad. It's reasonable compared to the Intel microarchitectures. And it's a fairly big gain over Nios, so I think I will declare success here. All right, so here's the summary of the first part of the talk. So I designed a microarchitecture and a bunch of circuits for an out-of-order processor. It supports both system and user modes. It's much bigger than a Nios, but it's also actually pretty small relative to an FPGA because FPGAs keep growing exponentially, and Nios really hasn't changed in 20 years. And it does get a significant performance boost. So I think I'm demonstrating that out-of-order can work on an FPGA, and even x86 is feasible.
Summary level, what was power consumption?
I did not look at power consumption at all. So Fmax was my primary design goal. And I just observed area. All right, so in the second part of the talk, I'm basically going to go through the processor pipeline from fetch down to commit and talk about what I think are the interesting designs at each stage. Something to keep in mind is that my timing budget is basically 5 logic levels, which is about 3.5 nanoseconds. So you'll see that a lot of the circuit designs were very carefully designed to try not to exceed 4 or 5 logic levels just to hit my frequency target. And a lot of the circuits were designed bottom up instead of top down. So I started with little building blocks and tried to make them bigger instead of here's this giant piece of RTL, let's synthesize it to a block of hardware. Okay, so let's start with at the beginning. So the front end of the processor is instruction fetch and decode in 32-bit x86 code on the benchmarks I ran on it. The average instruction length is about 3.4 bytes. So if I wanted to sustain 2 instructions per cycle, I think fetching 8 per cycle is probably good enough. So I decided on fetching 8 bytes per cycle. x86 is really annoying in that you don't really know the instruction length until you've read the instruction. And x86 has these things called prefix bytes, where you have an instruction, but you can add bytes before the instruction to change the meaning of the instruction. So if you just follow this rule, there is actually no limit to the length of an x86 instruction because you're allowed to have repeated prefixes. There is a rule that says if you exceed 15 bytes, it's just considered wrong. But other than that, there is no length limit. So you have to conceptually, you have to sequentially scan through every byte of the instruction to find out all the prefixes before you figure out the length of the instruction, and then you can start reading the next instruction. So it's really hard to parallelize instruction decode if you don't know the instruction length. So the observation here is that on 32-bit x86 code, 86% of instructions have no prefix bytes, and 14% have 1 prefix bytes, and almost no instructions have more prefix bytes. I've seen 7 prefix bytes, but it is extremely rare. So that means that I chose to design the decoder so that it would be able to handle up to 1 prefix byte with no penalty. So that means it's really looking at 2 cases. There's either no prefix byte or 1 prefix byte. We'll handle both cases in parallel. If it satisfies this, it can decode 2 instructions per cycle. There's a penalty if you exceed the number of prefix bytes, but it still must handle this correctly. So it sequentially scans through the prefix bytes if you exceed 1 prefix byte. If you go 64-bit, this will have to change because the number of prefix bytes actually goes up a lot. So 3 becomes fairly common, I think, or 2 prefix bytes becomes fairly common. Next stage, once you decode the instructions, you have to decode them into microops. In my particular design, my microops were actually fairly powerful in that they both contained a arithmetic operation and a memory operation. So they looked a lot like regularized x86 instructions. They don't look like RISC instructions. So as a result, the number of microops is actually very small. 94% of the time, 1 instruction maps to 1 microop. So this handles all of the register memory addressing modes in a single microop. They are scheduled and executed separately, but they are treated as 1 microop in the front end. And more than 1 microop is quite rare. So we'll put a cap of, we'll be able to sustain the full decode throughput if your instruction decodes into 2 or fewer microops. There's a penalty if you exceed that. So in x86, the worst case is pretty difficult to deal with, but the common case is actually quite straightforward. Okay, so now that we have microops, the next stage is register renaming. So register renaming takes all of the logical register numbers. So in x86, there's things like EAX, EBX, ECX, and maps them to the physical register number that's actually in the microarchitecture. So it turns out we have to map a lot of registers per clock. In the worst case, a instruction can have 7 registers referenced. So that means I have to rename 14 source operands per clock. So that's not just general purpose registers. So because there's a memory operation, there's arithmetic, which takes some sources. The address can take some sources. There's also segmentation in x86, so you have to rename that as well. There's condition codes in x86, so that's yet another source. So it comes up to a lot of sources, but you can pretty much do them all in parallel. So another interesting design here is that I decided to give each execution unit its own physical register file. So this is not a centralized register file. The reason is, if you remember way back earlier, multi-ported RAMs were very expensive. It's multi-ported write ports that were very expensive. So in this design, if each arithmetic unit has its own register file, each register file only needs one write port because it can only be written by that execution unit. But now the trade-off is your register renamer now has to track which register file is my operand in. And it also makes it's also somewhat unbalanced in that if you execute a lot of operations on one execution unit, then all the operands end up being in that register file, leaving the other register files underutilized. So the trade-off here is you save multi-ported RAMs in exchange for wasting register file capacity. But multi-ported RAMs are expensive, but single-ported RAMs are cheap on an FPGA, so this is a good trade-off here. And the way we do this is by hacking the register renamer to track where the operands are. So this is the renamer circuit that I ended up with. It's pipelined over 2 stages. The first stage basically checks all the dependencies between the two microops being renamed in that clock cycle. And that decides all of the mux select signals, and in the second stage is just a whole pile of muxes. So what else do I have to say here? It's fairly fast. It's not all that big. x86 actually makes the register renamer easier to design because it has so few registers. So there's only 8 general purpose registers. I think I expanded it to 11, including temporaries. So it was cheap enough that I could make the entire register renamer out of lookup tables, and I didn't have to make a SRAM block to store the renaming table. So if I had to do this on a RISC-like architecture with 32 registers, the renamer would actually be much more expensive. So after renaming, the microops get sent to an instruction scheduler. So the instruction scheduler stores all of the operands and tracks whether the operands are ready. So all it's doing is saying it will pick the earliest ready instruction and send it off for execution. Once it's executed, it'll track that the destination has been produced and some new instructions might become ready. So this is just tracking the data flow of the instructions that are in the scheduler. And it just keeps doing that repeatedly. So scheduler size traded with circuit cost. The scheduler size affects how much parallelism you can extract. If you have a large scheduler, you can look further ahead in the instruction stream, and that gets you more instructions per cycle. So here is a plot of achieved instructions per cycle versus the size of the scheduler. And I was kind of greedy, and I chose to use a size 32 scheduler, although you might say, you could probably get away with 24 without giving up too much performance. So we're trading off capacity for Fmax and area here. And 32 gets me 275 megahertz, so that's good enough. So I'm going to take that. So the scheduler circuit looks like this. It's a 4-way distributed matrix scheduler. So 4-way distributed means there are 4 execution units in my processor. Each execution unit has its own slice of the scheduler, which means microops that are executed on a particular execution unit must go in that scheduler. So that means that it's more easily to get imbalance in the scheduler. In a unified scheduler, which I think Intel likes to use, all microops go into the same pool, so it's less likely to overflow. But the trade-off is that with distributed schedulers, each slice of the scheduler is smaller so you can make it faster, but you get less efficient utilization of the entries. So I decided with four-way distributed. It's a matrix scheduler, so matrix schedulers are kind of interesting. So normally when you think of a scheduler, you think of a micro-op and it has operands, and you track whether the operands are ready or not. You will compare tags. When you execute an instruction, you broadcast the tag, and the tag says this operand number 3 is now ready. A matrix scheduler doesn't track operands. It actually tracks dependencies between instructions directly. So instead of storing this instruction requires operands 3 and 5, it says this instruction is dependent on previous instructions number 6 and 8. So it tracks whether the instruction is completed rather than whether the operand is available. And that it's a matrix because if you draw it out the circuit, it actually looks like a grid of wires with a single flip-flop and an AND gate at each intersection point. So matrix schedulers are faster when they're small, but they grow quadratically in size. They're basically a big matrix. So for smaller schedulers, matrix schedulers are faster. So at 32 entries, it's still considered small, so I went the matrix route. If the scheduler were to grow significantly, I might choose to go back to the more traditional CAM route because it scales better. So I chose 32 instructions. I chose a size 32 scheduler. For comparison, the Pentium Pro had 20, and Skylake, which is fairly recent Intel processor, is 97. So it gives you an idea of roughly where my design sits. All right, so we're going to look a little bit more closely at the one of the picker circuits for a scheduler. Okay, so the purpose of the picker circuit, the job is I have a bunch of instructions, micro-ops. Some of them are ready to be executed. This circuit's job is simply to pick the first one that's ready and send it off for execution unit. It's a very simple circuit. So, in this diagram, I have a bunch of zeros and ones. Ones means ready, and the output of this circuit is I just want the earliest one. That's all it has to do. Turns out this circuit's actually kind of slow in an FPGA because FPGAs don't have really wide logic gates. It can only do 6 inputs. So the circuit that I came up with is based on some past work on adders. It's a prefix tree that's logarithmic in depth. I forgot how to explain this. Anyway, it's called a Han-Carlson prefix tree. It's used in adders. The end result is basically that this structure, instead of being linear in delay, it becomes logarithmic in delay. Because it's an FPGA with 6 input lookup tables, I chose to use a radix 6 prefix tree. I think if you built this on silicon, most people choose radix 2. So FPGA is a little special because 6 is not really more expensive than 2. And one real difficult thing that I encountered was the logic synthesizer actually wants to tear up my radix 6 tree and make it linear again. So I had to spend a lot of effort fighting with the synthesis tool.
So rest of the prefix tree?
Yes.
Convert it into it?
Yes.
Wow, that's an anti-optimization.
It's linear uses less area. So I think it was doing something like common sub-expression elimination. It often makes things slower. Okay, so after scheduling, the micro-ops get executed. My processor has 3 different execution units. The AGU is for memory operations. It computes the addresses. There's a simple ALU and shifter that executes in single cycle and only for the simple instructions. And then there's a longer 3-cycle execution unit for all the other things that couldn't fit in a single cycle. So I think the single cycle ALU is probably the most interesting from a circuit perspective. So we're going to look more closely at that. So the single cycle ALU is actually composed of 3 separate parts. There's a shifter, there's an adder, and there's bitwise logic for things like OR and so on, bitwise. So we're going to look at the shifter and the adder circuits. So let's start with the shifter. So shifters on FPGAs are rather inefficient. As we saw before, multiplexers are inefficient on an FPGA, and a shifter is really just a whole pile of multiplexers. So we have to spend a lot of effort to figure out what's the most efficient way to build a shifter. So this is probably, if you had to shift a 32-bit operand, this is probably pretty close to optimal. A 6-input lookup table can implement a 4-to-1 multiplexer, which means you need 3 levels of logic in order to do a shift. I don't think you can improve on this. So what I did was, starting off with that data path, I added a whole bunch of control logic to make the shifter be able to do left and right shift at 3 different operand sizes and rotations and a whole bunch of other variations like byte swap and sign extension, everything that looks kind of like a shift, and crammed it all into a data path that was 3 levels of logic, except for a few small control paths. So the critical path was still on the three logic levels. So as you can see, the interesting part is if you look at the control side on the left, the control was designed such that the first level of muxes have 0 levels of logic for the control, and there's more and more control for the later levels of the data path. So I managed to pack a lot of different x86 specific shift operations into the basic data path without really extending the critical path by very much. So the end result here is that this particular shifter circuit is 50% faster and 46% smaller than if I simply wrote the same operations in HDL and let Quartus synthesize whatever it wanted. So basically, you can quote a case statement and say, I need to do all of this. All right, so now we're going to look at the adder. So on an FPGA, there are hard carry chains for adders. And it's really, really hard to improve on that unless your adders are, thousands of bits long. So the hard adder is pretty much, you can't improve on it. It's basically optimal for 32 bits. But what we can improve is x86 says we need to do an addition, but there's also a 0 flag. And the 0 flag says, is the result 0 or not? And on an FPGA, you don't have wide gates. So a 0 flag is basically a NOR gate with 32 inputs, and that requires 3 levels of logic. So now what we have is the 0 flag computation costs just as much as the adder, but it's also in series with the adder because you need the result. So we don't like that. So it turns out that you can actually compute whether the sum of 2 numbers is equal to a constant without using a carry chain. And this was done many, many years ago using sum-addressed caches and things like that. So this is an existing technique, but hey, we can apply it here as well. And now we can compute the addition in parallel with computing whether the addition is equal to 0, now in parallel instead of in series. So it's still 3 logic levels, but now they're in parallel. So this circuit is 24% faster. It's not quite as impressive. It's also bigger because you're now the 0 flag computation is more complex. But it's 55% area increase, but it's really only 30 logic elements, out of 27,000. It's not much of a price to pay, I think. So we're gaining some speed. Okay, next section. Now I'm going to talk about the memory system. So the memory system is basically the whole system that does loads and stores from memory. And from my experience, this is probably the single hardest component of the processor. I think I spent about 2 years on this part alone. It's kind of ridiculous, and it's not really x86 specific. So memory operations are basically loads and stores. In x86's case, we decode them into microops, and the microops basically are loads and stores. So the design's basically the same, regardless of whether it's x86 or RISC. It's loads and stores. So it's not just a unit that goes to memory. For performance reasons, we need caches. And there are a lot of caches. There's data caches, there's instruction caches, there's also caches of the page table. So, you end up with something like 2 TLBs, 2 data caches, and an L2 cache. So you've got a whole bunch of caches in the system. So when you have caches, you have the very classical cache trade-offs. In this plot, I show 2 of my benchmarks, Drystone on the left, SpecInt on the right. I show these 2 because Drystone basically doesn't touch memory at all, so it's not very sensitive. SpecInt touches memory a lot. So these are basically the 2 extremes, just to show you 2 types of extreme workloads, what happens when I play with the memory system. So a very classic result is, as you increase the cache size, your performance improves. Drystone doesn't touch memory, therefore it doesn't care, so performance doesn't change when you change the cache size. L1 caches have to be small because we have to be able to build them. So we ended up choosing 8 kilobytes, which is quite small. And we're giving up quite a bit of performance by choosing something this small. But it turns out you can get most of this back by having an L2 cache. So we also added an L2 cache, and of course Drystone doesn't care either. But in addition to the very classical just cache size trade-offs, when you do out of order, there's a whole bunch of other fancy things you can do to the memory system. Things like how many concurrent misses can you support? If you are handling a cache miss, can you keep executing independent instructions and execute more cache misses in parallel? So now you can get memory level parallelism. Can your memory system support out of order execution? A lot of earlier out of order processors did not execute memory operations out of order because it was very difficult to track dependencies between memory operations. So if you have a store followed by a load, is this load dependent on the store? It's hard to figure that out. So it turns out at least for my processor, these other techniques also get you some fairly big performance gains. So I ended up choosing the far right data point. So my memory system is out of order. It also does memory dependent speculation. So it will speculate whether loads are dependent on stores and then flush the pipeline if they were and I thought they weren't. How much time do we have? 5:30. Okay, we don't have much time. Okay, so here's a summary of the L1 memory system, the data side only. So we have data cache and tags. We have a TLB. The MSHR is miss status handling register. This is for tracking the outstanding cache misses. And then we have a store queue for stores. So the critical path of this is whenever you do a memory access, for example, a load, you first have to do an address translation. And then after you get the translated address, you have to compare it to the cache tags to see whether you've hit in the L1 cache. And then if it does, you have to select out which bytes of the data you actually want from the loads. So just a reminder, x86 does not require aligned accesses. So you do need a rotator after the data array. So one optimization I did here was this is a fairly long critical path. If you replicated some of the logic, it turns out this critical path can be made shorter by pre-computing both. So it's a two-way TLB. So we pre-compute both answers, assuming it hit in one way or hit in the other. And then we select the correct answer at the output. So this is a trade-off of we spend more area in order to decrease delay. So I'm going to skip over this. This is the horrifying version of the previous slide. It goes through all of the many ways a single load could fail and how you handle it. Okay, so this is the final circuit level diagram of the same circuit I showed you in the previous slide. It's a very complicated diagram, and I don't think it's clear exactly what you're looking at. So the important thing to notice here is that the critical path is through the TLB and translations. It's 4.3 nanoseconds. It's interesting to note that there are a lot of other critical paths that are very close in delay. So this is a very highly optimized hand-tuned circuit such that a whole bunch of different paths have very similar delay. So the blue boxes are 6-input lookup tables. So basically all of this circuit was all hand mapped to lookup tables, and it was all designed so that all of the critical paths go through exactly 5 lookup tables. So the end result is that the whole memory system is about 4.3 nanoseconds in delay, and if you compare it to the same memory stages on the Nios, on the Altera soft processor, they actually have a much simpler memory system. And they take longer. They take 6 nanoseconds to do the translation and cache access. But they split it over 1.5 cycles, whereas I pack it all into a single cycle. So I'm trading a lot of hardware for increased delay. All right, so we've reached the end of the second part of my talk. So I'm concluding that out-of-order processors are useful and feasible. They are big, but they can get you performance, but only if you pay a lot of attention to the circuit level design and not give up 50% of your clock speed. So you can do that either by making microarchitecture choices that suit the substrate that you're building on, or you can spend a lot of effort designing the circuits to implement your microarchitecture. And I found that LUT-level design is actually often quite useful, but also painful because the logic synthesizer often undoes your optimizations. So unfortunately, the processor isn't actually finished, so it's still a collection of pieces right now with some pieces still missing. I think there's still some hope that the memory system could be optimized for further frequency by adding an extra cycle. And the fact that this processor was missing a floating point unit was extremely painful, so I certainly hope to add a floating point unit sometime of any performance level. The emulation mechanism for the FPU was much more painful than actually having an FPU. That's my conclusion here. All right, so that's the end of my talk. Questions?